right here, and it's been a nice workshop. So this talk's going to complement Linda's talk a bit. We're talking about some methods for how to prove classes are chi-bounded, or how to prove some classes are paradigmatic. I'm going to do the opposite and talk about some methods and constructions of graphs of large chromatic number. Classes of unbounded chromatic number, or they're not chi-bounded. Okay. So we've seen this very obvious example of a graph of large chromatic number of this cliques. Every vertex in a clique needs its own distinct color. But this isn't really an interesting reason for a graph to have large chromatic number, and this is where this notion of chi-boundedness comes from, like asking if you have bounded chromatic number when you bound a clique number. So I want to talk about some more interesting constructions of graphs of large chromatic number, which are either triangle free or at least have bounded clique number. And we know that there are triangle free graphs with large chromatic number, classically proved by Tart. Okay. So I want to go through a few different constructions and methods. So a lot of these I'm only going to like briefly show, because I can't go into detail on all of these, but hopefully you'll at least be aware that these methods and constructions exist that can do certain things. So can remember these constructions exist. That's enough, even if you can't remember what they are. Okay. So most I'm not going to spend much time on, but Tut construction is a construction which is like, there's a lot of ways to alter and a lot of variants you can make for this construction. It's very flexible. It's been very useful recently. So this one's quite fun, and this one I'll go into more detail on towards the end. So these other 5 I'll only cover kind of quickly. That's construction we'll go deep into. Okay. So there's these probabilistic method, and in fact, the probabilistic method was introduced by Erdos for a construction of graphs of large chromatic number. He constructed graphs of large girth and large chromatic number. So girth is the size of your sorted cycle. So this is much stronger than just showing this triangle free graphs of large chromatic number. So some advantages of a probabilistic method for constructing graphs of large chromatic number is that one is quite economical. Right. One advantage is that the way you prove it as large chromatic number is that you're actually proving a boundary independence number. But this is something stronger than large chromatic number, because if you only have small independent sets, this means each color class is small, so you have to have a big chromatic number. The boundary independence number is stronger. Another advantage with these probabilistic method constructing of graphs of large chromatic number is that they tend to be quite economical. They don't have too many vertices in general. So, for instance, one nice application is that you can construct triangle-free graphs of intersection graphs of lines in free space that have this polynomial chromatic number, n for 1/15. And there's a very nice proof of this by Van Tommen. So it's not just like things like just only high girth you can get. If you're in some class where you can find some clever way to look at some random graphs, then probabilistic method is a good idea to look at. And this is a nice proof. Okay. Another classical construction is Kneser graphs. So these are these graphs where we're looking at an L-element set, and our vertices are going to correspond to K-element subsets. And we have an edge whenever our K-element subsets are disjoint. So to have any edge, we need n to be at least 2k, and we're not going to contain a triangle if n is less than 3k. And then this very classical theorem that if we're looking at this n-element set and k-element subsets, nk Kneser graph, then we have chromatic number n minus 2k plus 1. So one very cool thing about this is that actually it has a very topological proof of this high chromatic number. It uses this theorem from topology that you've probably all seen at some point, that if you have a continuous function from an n sphere into n space, then some antipodal points are mapped to the same point. So without going into it, it looks like magic that you could apply this. I'm not going to go into it, but it's a really beautiful proof and it's worth looking at. So one nice property about these graphs is that actually this is like the classic example of graphs with small fractional chromatic number and large chromatic number. So you can show that they are fractional chromatic number n over k. Another nice thing about these graphs is you can't get large girth because you've got these big complete bipartite graphs in them, but you can get large odd girth. So odd girth is just the length of your shortest odd cycle. So if you take n to be not too much more than 2k, but still a high constant amount more, but as a fraction, not too much more, then you're still going to get high chromatic number by this theorem, but you're not going to be able to find short odd cycles. So this is a nice construction for having large odd girth as well. Okay. By the way, feel free to stop me for questions at any point. I won't throw anything at you.
He actually asked me to throw things at you.
I bet I won't. Another classical construction of triangle free graphs with large chromatic number is shift graphs. And one way to view these is kind of like as line graphs or directed graphs. But the classical definition is that you're looking at pairs between 1 and n, pairs AB, B greater than A between 1 and n. These are going to correspond to our vertices. And then AB is adjacent to CD if B is equal to C. So if you just had this as like a line graph or a transitive ornament, that's like how vertices correspond to these directed edges, and then they're adjacent if the one going in is going into the tail of another edge, and you add an edge. So shift graphs are essentially line graphs of directed transitive ornaments, and you can generalize this for line graphs of any directed graph. So this was shown that these are a construction of triangle free graphs with large chromatic number. One easy way to show that they should have increasing chromatic number is you take n to be some huge number, you apply multicolor Ramsey, find some monochromatic triangle, and that's going to be an edge between two guys that are adjacent. You can have better proofs than that, but that's one quick way to see.
So James, you said you could view it as line graphs of directed graph. Is there like a simple condition the directed graph would need to have to ensure that the line graph has large chromatic number?
Yeah, so the chromatic number are tied by some functions.
Okay.
So if your directed graph is, it's got to be acyclic. But anyway, if that has large chromatic number, then your line graph will have large chromatic number.
That's not necessary because this has tournaments of small chromatic number, yeah.
Yeah, but these contain those guys as like reduced subgraphs. So one thing it's good for is you can reduce the graph with large odd girth this way. Because if this original directed graph had large girth, then a line graph will have high odd girth.
Why would you want high odd girth?
So it's not quite as nice as having high girth, right? It still says that locally you have bounded chromatic number. So it means you have large chromatic number for still a non-local reason. So in a slightly weaker sense than high girth, but still locally bipartite.
The growth of the chromatic number?
So,
What is the growth of the chromatic number?
so for these guys, it's log n. The proof I said with multicolor Ramsey isn't going to get you log n, but you can come up with a better proof. Okay. Yeah, so these large odd girth variants are these line graphs. There's also some variants when instead of looking at pairs, you look at triples or n sets. Okay. Another method is you can actually apply algebraic methods using this theorem, which is it's very strange when you first look at it. Not talking about eigenvalues, and we're getting some chromatic number bound. I'm not going to go into detail, but I'll talk a little bit about why something like this isn't completely crazy. So this is Hoffman's ratio bound, and it says if we've got a k-regular graph, then we can get a lower bound for a chromatic number by graph in terms of k being k-regular and the size of our minimum eigenvalue. So for eigenvalues of a graph to make sense, we look at its adjacency matrix. our columns and rows are labeled by our vertices, and we have a 1 if there's an edge between these corresponding vertices. So looking at eigenvalues of a graph is something you can do. And then this isn't completely crazy, because this chromatic number bound comes from bounding the size of an independent set. And an independent set, if you look at an adjacency matrix, this is like a all square zero matrix. So once you see that, this is still pretty amazing, I think, but it's not so crazy that you get some kind of chromatic bound from using linear algebra. So the bound we get is just 1 plus k for k regular divided by the negative of a minimal eigenvalue. And again, this is actually a upper bound on independence number it gives, so it's stronger. So you can ask, well, when is this likely going to be useful for saying some graph is large chromatic number? If you showed me some random graph, I have no idea how to compute eigenvalues of this thing. But if you've got some nicer vertex transitive or even better Cayley graph, then now this is something more reasonable to look at eigenvalues of. You can apply some stuff from group theory and have some idea of the value of the eigenvalues. So if you're in some world where you have vertex transitive graphs, it makes sense to try and look at Cayley graphs in this and try and apply these algebraic ratio bound theorems like Hoffman's ratio bound. So to give one example of a graph you can get in this way that has high chromatic number, is you can look at a Cayley graph over the rational squared with these generators. So the generators are just going to be odd multiples of, in one coordinate you've got 2 to the t, in the second 2 to the minus t. In one coordinate increasing powers of 2, in the other decreasing. And this doesn't directly apply because this is an infinite graph, but essentially using these kind of methods, you can prove that this guy has infinite chromatic number. And this also is triangle free. One nice application of this stuff is that you can prove this theorem in Euclidean-Ramsey theory, that if you have a finite coloring of a plane, you can always find a monochromatic pair of points whose distance is odd. This isn't immediate from this stuff, but essentially the same kind of methods you use for this, you use to get this somehow. So you can go back and do stuff with in geometry with this stuff as well. So these odd distance graphs is vertex transitive. It's one reason it makes sense to look at these Cayley graphs. Okay. Another construction that I really like a lot is Berlin graphs. And these are a bit more complicated to show. They have large chromatic number, or the construction's a bit more complicated than things like shift graphs. But really, Berlin graphs appear to be surprisingly fundamental. I won't get into what that means, but it appears they're not just randomly counterexamples to chi-boundness of classes. It appears often they really turn up for a good reason. But these are really important constructions of large chromatic number. Okay. So the construction is going to be one of these inductive constructions where we start with some Berlin graph BI, and we're going to inductively make the next Berlin graph BI plus 1. And somehow we want to bump up the chromatic number of this. So we're going to actually prove something a little stronger in having a large chromatic number. Instead of only keeping track of our ith Berlin graph BI, we're also going to have some special independent set of vertices, this Si, and they're going to have this property that in any finite coloring of our Berlin graph, or any coloring even, we can find one vertex in this special set of vertices so that their neighbors see at least I-1 or N-1 colors. And this will hold for like any coloring, not a bound number of colors. But this again, because some guy sees at least N-1 colors, just going to give a low amount of N for chromatic number. Okay. So we can just start off with a third Berlin graph. This is going to be just this bicycle. And our special set of vertices is going to be these two. So first we can check that it satisfies this theorem. Well, one of these two guys has to see at least two colors in any coloring, because maybe this guy only sees one color, but that means this guy has to be the same as this, so blue. But now this guy is adjacent to that, so it has to be some new color green. And now our second vertex here, these two of different colors.
So this is B3 now.
This is B3. And then I want to say how you construct BI plus 1 next. So I'm going to be making B4. So the idea is that we're going to have lots of copies of BI, and we're going to connect them in some special way to make up BI plus 1. So we're going to start with some central copy of BI, or B3 here. And for each of these special vertices, we're going to add on another copy of BI. So this guy's got his own copy of BI over here. This guy's got his own copy over here. And each of these we're going to attach onto their own personal copy in some careful way. So the first thing we do for this attachment is we're going to look at this special vertex and this corresponding copy. And for each special vertex here, we're going to make a copy of two of these guys. So we're just cloning this vertex. We've now, instead of one of these guys, we've now got 4. So 2 for each of the guys up here. And then we're going to connect them. So each guy up here gets a pair. So for one, we're just going to give the same neighbors as this guy previously had. And for the second guy, we're just going to add an edge to the active guy in the copy and make it inactive. So this guy's no longer special. So let's go through it again. We'll make copies of this, 2 for each special active vertex. Then we connect them, one by giving the same neighborhood, and one by making the remaining pair adjacent and making this guy inactive. Okay. And I'll do the same thing here. Now my claim is that this special coloring property holds. I'm now going to find one of these special active vertices which sees at least 3 colors when I look at a coloring. Okay, so I can look at a coloring, and for now I'll just focus in on this central copy of BI. And I already know that one of these 2 old red guys is going to see at least 2 colors. So let's just say it's on the right hand side again. This is going to tell me which copy of my BI I want to now focus in on. So now I just need to look onto this copy I attached to. And I can do the same thing here. But one of these special guys is going to see at least 2 colors in here. So let's just say it's on this side. Now I have this vertex which sees at least 2 colors in my central copy and 2 colors on the attached copy. If these weren't the same 2 colors, then I've won, because I'll be seeing at least 3 colors now. So I can assume they're the same color, blue and green again. But then I've got this guy here who sees the same neighbors in this copy of BI as my active vertex. So he needs a new color. He needs some third color disjoint from this blue and green. So he needs something like orange, say. But then this is why I attached this guy with a matching edge. This guy sees the original 2 in my central copy still. And he sees this new third color. So doing this, I am bumping up the chromatic number each time. I iteratively do this now again for each active copy and make B5. This will have chromatic number 5. Okay. So some nice things that Berlin graphs have been used for is, I think the nicest is showing that string graphs are not chi-bounded. So string graphs are intersection graphs of curves in the plane. So they're kind of like the most general class of intersection graph you can have in the plane. These guys show that they're not chi-bounded. And one nice thing from that example is that you forbid things like induced subdivisions. You can't have any subdivision of, well, one subdivision of K5 as a string graph. So this also disproved the conjecture of Alex Scott that graphs without a forbidden induced subdivision are chi-bounded. the Berlin graphs are particularly good at is proving these chi-bounded conjectures where you're somehow forbidding some very induced minor kind of thing. Okay. For now, I want to talk about my favorite construction of graphs with large chromatic number, and this is what I'll spend most of the talk on. It's this Tut's construction. And similar to Berling, this is going to be of the style of, I've got lots of copies of I've got my n chromatic graph already. And I want to construct I want to bump up a chromatic number and make a graph with chromatic number n+1. And I'm going to do this by somehow attaching lots of copies of my previous n chromatic graph together in a certain way. So let's just say I start off with something easy, this 2 chromatic 3 vertex path. I want to show how I'm going to bump this up to a 3 chromatic graph. And I'll be maintaining that we're triangle free. So for this construction, I'm going to start off with a large independent set of vertices. And now my previous graph had 3 vertices. So I'm going to look at each subset of 3 vertices down here. So say I look at these 3 first. And I'm going to add on a copy of my previous n chromatic graph and attach it onto this subset with a matching. And I'm going to do this for every single 3-element subset here. So I can look at this subset as well. I'll attach another copy of my guy here. And I do these for every 3-element subset. Okay. So why is this going to bump up a chromatic number? Well, assuming I chose this independent set to be big enough, which in this case I did to get to 3 chromatic. If I suppose it has chromatic number less than 3, so I suppose you can 2-color this guy, then because I have 5 vertices down here, in any coloring, some 3 of them need to be the same color. So I looked at this red-green coloring. I know I can always find one monochromatic set of 3 vertices of the same color. But now I can look outwards and look at the guy I attached on here. Now, if I want to finish off my coloring, none of these guys can be colored red anymore. They're all adjacent to these red vertices of the same color. But now this is going to bump up the chromatic number by 1 because I have 1 fewer colors available to color this guy. So here, this shows me that I go up to chromatic number at least 3 because I cannot color this guy with 1 color. Okay. So the other important property is that we're maintaining that we're triangle free. We're building cliques. So I want to look at what happens. So clearly we started without any triangles. So if somehow we introduced a triangle, it must have been made by going in and out of these independent vertices. So here we don't have a triangle, but we've got a 6 cycle, for instance. But because you need to go in and out at least twice, we know we're never going to make a triangle. But we could make a 6 cycle, for instance. Okay. So I want to show you one more example of a chi-banded class, which are rectangle intersection graphs. So we're looking at axis-aligned rectangles in a plane. Each rectangle is going to correspond to a vertex, and the vertices are adjacent if their corresponding rectangles intersect. So this configuration of axis-aligned rectangles, rectangle intersection graph. A nice classical theorem in chi-boundedness is that rectangle intersection graphs are chi-bounded. Now, one thing you might hope to be true is that this always happens in any dimension. So going up to 3 dimensions, we can now look at box intersection graphs of axis-aligned boxes in free space. So these boxes will give you this box intersection graph in the same way that it works for rectangles. Unfortunately, it's not true that these are chi-bounded. And actually, this is where Berling's construction originates from. Berling using Berling graphs, so that box intersection graphs are not chi-bounded. This triangle-free box intersection graph with a large chromatic number. So you might hope that something weaker is still true. You don't have chi-boundedness, but maybe if you increase the girth, you could get bounded chromatic numbers. So it was asked if you have large enough girth for box intersection graphs, then do they have bounded chromatic number? But actually, this isn't the case. Using some special variant of Tut's construction, we can make box intersection graphs with large girth, large chromatic number. So I want to spend the rest of the talk talking about variants of Tut's construction and then how to apply them for box intersection graphs. So to do this, I want to first go back and look at Tut's construction from a different perspective. So what we were doing before is we had this three vertex graph we're adding on to our big independent set. Every three element subset we're adding on to. But we could kind of view this as some auxiliary hypergraph. So we're adding on to every three element subset of a five vertex set. This is like having a complete three uniform hypergraph on five vertices. And for each hyperedge, we're adding on a copy of our previous graph with a matching. So, like so, we've got some hyperedge. And for each, we're adding on our three vertex path of a matching. Okay. And then why does this work? Well, we saw before it bumps up the chromatic number because we find some three vertices of the same color if we two color it. What this is actually saying is that this hypergraph has chromatic number more than three. If we two color it, then we can find a monochromatic hyperedge. This is the condition we're using when we abstracted hypergraphs. So in the two coloring, we find this monochromatic hyperedge. And we knew we're adding on a copy of a previous graph to this. And that's exactly what bumps up the chromatic number. Okay. And we can also see how we're creating cycles somehow here. We saw before how we could create a six cycle like this. Well, really, where this six cycle was coming from was that in our hypergraph, we've got this two cycle. It's made from these two hyperedges. Whenever we go into a copy, we need to go in, along, and out. So this is at least three. So actually, looking at it this way, we're constructing graphs with girth at least six, not just triangle three. Okay. So this hypergraph perspective gives us an idea. We don't have to just use complete hypergraphs. We don't have to constrain ourselves to that. We can be more creative. So for instance, we could look at this hypergraph coming from a Fano plane. Hypergraph with these vertices and these hyperedges. And we do exactly the same thing of attaching on hypergraph. So this hypergraph has chromatic number 3. In any two coloring, we can always find a monochromatic hyperedge. Like so. And free color it. And one thing that's different is that we don't have two cycles anymore. We don't have any two hyperedges sharing two vertices. We do have a free cycle, but we don't have two cycles. So now our hypergraph is girth free. So in general, we can do better in this. Classically, again, the first construction of probabilistic method, we know that there's uniform hypergraphs with too large girth and chromatic number. So one way of altering Tut's construction is we can always use these high girth, high chromatic hypergraphs instead of every single subset. Okay. And as before, we're adding on a copy of a previous graph for each hypereds. You look at a two coloring, look at its hypereds, have the guy on, just bump the chromatic number up. And now we no longer have 6 cycles. We could have a 9 cycle because we have these 3 cycles, but we've still done better. Now our constructions are going to have girth at least 9. And if we use the high girth hypergraph, then our graph is going to have high girth. Okay. But this is nice, but for this geometric application of box intersection graphs, to get large girth, I do want to use some large girth hypergraph in my variant of task construction. But I want a particularly nice hypergraph that's suitable for these geometric constructions. So before I introduce what this hypergraph is, they're going to come from this very classical theorem that we're going to look at in Euclidean-Ramsey theory. So it's going to come from Galois theorem, but first I need to tell you what homothetic copies are. So essentially, if you have some set, a homothetic copy is just any copy you can obtain by translation and uniform scaling. So this blue star is a homothetic copy of this purple star. We just moved it along and made it bigger. This red star is not a homothetic copy because we've done vertical but not horizontal scaling. And this rotated star is not a homothetic copy because we rotated. It's this scaling, uniform scaling, translation. Okay, so it's a very pretty theorem of Galois says that if we have a finite collection of points in D space, and we finitely color our space, then we can always find a monochromatic copy that's homothetic of this P. You can find a copy of T obtained from scaling and translation that's monochromatic. So to give one example, we could look at the corners of a square in colorings of a plane. So this is my best attempt to have some ugly coloring of a plane. And this theorem says that we can find the corners of a square of the same color. So if you look very carefully, you can find 4 green points that are the corners of a square, which is guaranteed by Galois theorem.
Not just any square, an axis parallel square.
Yes, axis parallelism. Okay. And to relate this to a maybe more well-known classical theorem, is that this is essentially a generalization of van der Waals theorem. So this is this theorem telling you that if you have a finite coloring of the integers, you can find arbitrarily long arithmetic progressions. Well, this is basically like, there's a difference between a real line and integers, but it's not so meaningful. But it's basically like looking at if our set T was just some evenly placed points, like an arithmetic progression. This is just some scalings of your 1 to k, and translation, that's all an arithmetic copy. Well, that's all an arithmetic progression is only a homothetic copy of this guy. So van der Waals theorem is like a special case of Galois theorem. Okay. So really, you can just rephrase this kind of like Euclidean-Ramsey or thing on coloring of the integers in terms of a theorem about coloring hypergraphs. This is just really just looking at a hypergraph. So our vertex set is actually just like the points are R to the D, or we can restrict to some subset. And the hyperedges are going to be homothetic copies. So to rephrase Galois theorem, it says that for any of our, if we pick some finite set of points T in R to the D, then we can find some bigger set of points in R to the D, so that a hypergraph of homothetic copies of T on this set has large chromatic number. So Galois theorem is essentially giving you one construction of hypergraph of large chromatic number. Okay. So to give an example of this hypergraph, if we're just looking at homothetic copies of this 3-term arithmetic progression, and we're just looking at 5 points, we of course have this hyperedge translating along, this guy from translating, and one more hyperedge. This is just from scaling by a factor of 2 here, translating to a right spot. Okay. So hypergraphs coming from Galley's theorem, it makes sense that this would be helpful for some geometric application, some geometric variant of task construction. But if we also want high girth, we need a hypergraph coming from Galley's theorem to have high girth. And Galley's theorem does not guarantee this. So really what we need is a sparse variant of Galley's theorem, which does exist. So you can actually pick your set of points in R to the D, which we're putting our homothetic copies hypergraph on, so that now your hypergraph has large girth as well as large chromatic number. But this theorem strengthens Galley's theorem by saying that not only can you find these kind of geometric hypergraphs with large chromatic number, but actually they can also have large girth. So this lets us use them in task construction and also get high girth. Okay. So now I want to look at this geometric application of applying task construction. So we want to construct box intersection graphs with large girth and large chromatic number. And I'm going to give you this example again of how to bump up the chromatic number if all we're doing is starting with this 3 vertex path. These 3 boxes, their intersection graph is just a 3 vertex graph. And I'm going to show you how to bump this up. So we don't just want any randomly placed boxes. I don't know how to bump up the chromatic number of that. We want to prove something a bit stronger, something more restrictive than box intersection graphs. And this is just one of these arguments which now we have something stronger, and this makes our inductive argument, which we're doing with building up these graphs, smoother. So we don't just want these to be axis-aligned boxes in free space. We also want them to kind of lie on top of this hyperplane. This is just going to be, say, the x equals y hyperplane. And we want the back corners or back sides here to just be lying on top of this hyperplane.
Top.
On top. So if you looked at this side that you can't see, this is just going to be contained in the hyperplane.
I see.
So the rest of the box is kind of lying
So it's
to
like
one side. They're grounded on this hyperplane.
Okay.
Okay. So it's easy to see here. They're kind of grounded on these corners. Okay. So our plan's going to be to apply Galley's theorem. This is going to give us this hypergraph on some vertex set. Our hyperedges are going to be these it's going to be homothetic copies. Yeah. Large chromatic number. First, we need to pick what we're taking homothetic copies of. It doesn't make sense to just say these boxes. We need to pick some particular points. And actually, we don't want to apply this in free space. We want to apply this on a real line. So we're going to kind of look at this hyperplane from above. And we're going to look going along at where these boxes lie on a hyperplane. So we're applying Galley's theorem in a one-dimensional case on the real line. So to pick the points, we're going to like add this kind of like apparatus line, scaffolding of just these lines coming out from where our boxes lie on the hyperplane. And looking at it from above, this is how we're going to pick our set T that we're going to apply the sparse Galley to. So we're going to apply it to these 3 points on the real line. And then what this is going to do is give us some larger set of points on a real line, where a Galley hypergraph has large chromatic number and also large girth. So we've got each of these are going to correspond to vertices in task construction. we're gonna have to add in these vertices of boxes at some point. But we also need to add in homothetic copies of our boxes for these homothetic copy hyperedges. Okay. But this we can do. So we look at our original copy. And we're going to start adding in these homothetic copies. And we can do this. Well, a lot of them, all we're doing is translating along. We can also separate these vertically, agree to move it up and down these lines. So these copies are going to interact with each other. And we're also going to have these copies that are made from scaling and translations. But again, we can do this. We just scale up our boxes, translate them to where we want them to lie on the hyperplane, lying on these lines. And we move it up or down vertically, just to make sure these copies don't interact with each other. Okay. And then the thing we were missing was these boxes corresponding to our big independent set from task construction. So we kind of just, we remove our scaffolding with these yellow lines, and we're just going to place these long, thin purple boxes for our big independent set from task construction. So looking above, this can just look like something like this, piercing their corresponding boxes. Okay. And this is something we could keep doing. We can iterate if we, tiny technicality, we need them to lie on like different spots going along, but we can just move them a tiny bit. And if we wanted to iterate this, we do the same process. We now have chromatic number 3, so we want to bump it up to chromatic number 4. We add in these scaffolding lines. And now we're going to apply Galley's theorem to this much bigger set. So the graphs you get out of this constructions are very big because they rely on Galley's theorem.